Okay, it's 1 o'clock. Good afternoon, people. I'm assuming that you're hearing me. If not, well, maybe if you hear me and you can see my slide, just send a message or say something. For section 1, and in it I have people from both lab sections 51 and 52, and today right there. So what we have here is a steel disc made of steel with the information that's given, and the dimension that's given, and that's spinning about its axis at 113 radians per second. That 113 radians per second transforms into about 1,000 RPM. Now, you know that when this thing spins, we don't know how, we pretend that there is this magic thing that makes it spin. Okay, in real life, you know that that's not possible. This has to be inserted in a shaft. The shaft spins, and this thing goes with it. So it's not as simple as you see here with a nice round hole in it. Because to put the shaft in there, you may have to do shrink fit, or you may have to use keys and keyways to insert it in there. You may have to use the splines, etc. But we assume that magically this is turning by itself. Think about it as a UFO. Okay, somehow. Now, because of the rotation, the centrifugal forces will act, and this thing will shrink, will stretch in the radial direction, and of course it will shrink in the axial direction. When it stretches one way, it has to shrink the other way. Okay, because of the Poisson ratio effect. Now, this is why I have a density here, by the way, because in order to find the centrifugal force, you need its mass, or its density. You need its density more correctly. Now, first of all, so I have a question for you, and I hope somebody can would try to tell me if this thing fails. And when I say fails, the only criteria that we have at this point is called yielding. Because if things yield at a point, it's bad, because it's not going to go back to original shape when you remove the force or you remove the load. And usually you don't want that. You buy something, you play with it, you put a force on it. When you remove the force, you want it to go back to the shape that it was. Okay? So if that is our criteria, can you tell me where is the most critical point or points for this problem? It's actually on the inside face. Okay, around the small hole here, the biggest stress is in this area. This is why if you have cracks here, bad. If you have cracks on the outside, okay, it's not as bad. Let's put it that way. All right, so let's see why this is the case. Of course, we're going to run it. We do that. We'll run this thing. And in this problem, this is a classical problem. And the reason that we're doing it, we can get answers that we can compare with something that is theory. And if they match, we have this confidence that, okay, we know how to do FEA. If they don't match, means that either you're doing it wrong, or they made a mistake in the analytical solution, which is very unlikely for problems of this type. And okay. But in some problem, it may not be obvious. So I ask you here because it's a classical problem. In general, if it's something brand new, some design brand new, and you didn't use your, you didn't have to use your engineering judgment, etc., you won't be able to tell me. Okay. Now let me first say a few words about the plot that I'm going to be showing you in a minute. Now, if you stared at this thing along the axis, if you stared at this, and this was going at a constant speed, and you put a marker on it. Okay, you put a marker on it. You put a marker on it. Obviously, you know that this will trace a circular path. Okay, and as a matter of fact, if you put lots of markers on it, on a circle drawn up here, if you draw a circle up here and put some markers and let it go at a constant speed, and you stare at where those things went, you will see that they still go on a circular path. They are still on a circle, but a bigger circle, okay? Or let's look at it like this. If you draw a line here, draw a line with a marker, and draw another line radially outward with a marker, with an angle, say 30 degrees in between them, before it speeds up to 113 radians per second, and after it's still 30 degrees. Before it was 30 degrees because you made it 30 degrees. After, when it goes to a constant speed, that angle stays 30 degrees. This is why you don't have to model this whole thing. You can model a sector of it. 30-degree sector, 45-degree, 90, whatever you want, okay? And that means that this plane that you see here is a plane of symmetry, because you just told me that if you draw a line here, the points on that line go radially out. That's it. So they don't go side. They don't go side. They don't go to the left. They don't go to the right. That means this entire face is a plane of symmetry. It's a roller. Plane of symmetry means a roller. Nothing goes perpendicular to it. And the same on this face, surface slider. By the way, here you can also cut it in the middle. In the middle, you can cut it through the depth, and that is also a surface slider. That's also a plane of symmetry. Assuming that this is a uniform thickness disk, you cut it, that's a plane of symmetry. Now, in a problem like this, yes, it is true that you're going to say sigma x is this and sigma y is that and sigma z is this. So at each point in general, you have 6 components of stress. We know that. We know that. That matrix that you wrote down, 6 components of stress. However, 3 normal and 3 shear. However, in a geometry like this and a loading like that, instead of looking at those 6 components of stress, we can look at 3 magical directions. The 3 magical directions are the hoop stress, radial stress, and the axial stress. For example, if this is Z, sigma Z. These, in Dr. Green's class, was called principal stresses. So the 3 principal stresses in this problem at any point are actually given by these formulas. Poisson ratio is here, inside outside radius are here, and angular velocity and density. And you tell me a point, I know how distant it's away from the origin. I put a little r there, and I get the hoop stress, and I get the radial stress, and I get the axial stress. The axial stress, I hope you can see that it is 0, because when this thing freely stretches, it freely shrinks. And if it freely shrinks, there's no force in that direction that causes that deformation. And that's why the axial stress is 0. Sigma z is 0. There is a mistake in the drawing in the book, my book. This is the hoop stress. This is the hoop stress, hoop stress, hoop stress, tangential stress. This is the radial stress, which is also tensile. In the book, incorrectly is shown as compression. Now I want to show you a few things. Notice I asked you, where is the most critical place? You look at this hoop stress. Is that hoop stress? At the inside, it's 300, almost 300 psi. Radial stress is 0, because there's nothing pushing it radially outward. And radial stress started increase, reaches the maximum, and then drop. At the outer face, radial stress is 0. The hoop stress is never 0. On the inside, it's biggest. See that? Biggest, 0. On the outside, it's of some value. For example, from 0 to this is around maybe 50 or 70 or something like that. This was almost 300. The hoop stress never dies, but it's bigger on the inside, and therefore the most critical one on the inside. Okay. Are there any questions? Okay. I am asking you, and I'm watching the Wi-Fi connection here at the bar. Okay, because this morning, I'll come to you in a second, because this morning I recorded in the lab I recorded 40 minutes of it. I didn't realize that my internet was cut off. So the last 10 minutes I was talking in the screen and it was not recording. So okay. You start with a part file. So on this inside surface, the radial stress is 0. Nothing is pushing into it, right? Nothing is pushing into it. Okay, radial stress is 0. It goes to a maximum as you go out, and it go back to 0. Hoop stress, on the other hand, there is a hoop stress here. the biggest hoop stress is right here on the inside surface. And it reduces, it goes to a value here which is not zero. And the axial stress is in the direction of the axis of the rotation, and it's zero for all practical purposes. You will see that as we create the model and look at the plots. Okay, so we start with a part file. Don't start with product. Start with part. Immediately save it. File, save management, save as, on the desktop, create a folder. This is lecture section 1. Okay, lecture section 1. I'm going to put the stuff in here. There you go. Right there. And I'm going to give it a name that I can recognize. Follow the practice. 1, 2, 3, 4, 5, 6, 7, 8, 9. Your student ID. Last name, Timoshenko. Any identifiers. For example, lab, this is lecture, I don't know, lecture 1. Lecture section 1, that's what I mean. Any identifier, scrolling, rotating, disk, three planes of symmetry. Two on the side, one in the middle. Okay, good. Say okay. And we say okay. And we're going to make it. So on this vertical plane, I will draw a rectangle, and then I'm going to shaft it. So draw a rectangle. If you look at the problem description, it says the inside radius is 1 inch. So from here to here, this is 1 inch. Outside radius is 6 inches. From here to here is 6 inches. The height of this, because I'm cutting the disk in the middle, I'm making it 0.5. Notice that I could have made the actual disk and then use planes to cut it, just like you did with the other things, homework last week, etc. But you can also make the body just like it is. So this is what you want to do. There it is. And then we're going to shaft it. There is the shaft. There is the pad. There's the shaft. This is the rib that you have used. Shaft. That sketch, only 30 degrees. Along the axis, you have to select the axis. Put the cursor there, right-click, Z-axis. Yeah, good. Okay, fine. There we are. Okay. So I want to make this thing out of steel, metal, apply material. On that part, metal, steel, okay. In the event that you see that you're given an instruction to change the material, go and do it. Material properties. So analysis, you were told, analysis tab, you were told that this is 30 million, and Poisson ratio is 3. On the test, I'm not going to do it like that. I'll let you use the default properties of steel. You can even don't go too low because we saved. Now we're going to go to generative structure analysis. This is a static analysis. This is not dynamic. Yes, it's spinning, but it's not dynamic. Okay. Now, you want to look at the mesh? Look at the mesh. Right-click, mesh visualization based on that size mesh, which was default. And I'm pretty sure it's quadratic, parabolic. It looks like that. But you need a fine mesh here because just look at the distribution of your stress. The hoop stress changes from almost 300 very rapidly to something down. So you need a fine mesh here to be able to resolve. If you make a big mesh, you jump from there to there, basically. And you're going to miss all this action in between. So what we do need is a finer mesh in this area. So right click, first of all, deactivate the mesh. And you know how to do a finer mesh somewhere. There we are, local mesh size. I'm going to ask you on the test to refine somewhere. This tells you that you can do it, tells me that you can do it. I don't have to tell you by how much because I want to know whether you can do it or not. And there we are, okay? And if you now look at the mesh, you see that most of the stuff is on that size, but over here, look, see that? Okay, good. Now, I want to say a couple of words about when you do these things for living and they pay you to do it, is when you run an analysis, just like we will do here, even if you took a fine mesh here, there is absolutely no confidence on your results. What you should do is the mesh conversion studies. Just remember what I'm saying. Mesh conversion studies, if you are to get paid for these things, because you want to develop some confidence. In spite of the fact that you refined here, there is no guarantee that this is small enough. Okay, we're not going to do that. Deactivate this mesh. Now, this is surface slider. This is surface slider. And the bottom is surface slider. Now, some of you who may have looked at the book or have the book or got it, I don't know, or you will get it, and or you watch the videos that I'm referring to on YouTube, you notice that I say in the book and on those videos, I'm going to make your life harder. The easy way is to use surface for surface slider and do it like that. But I'm going to make your life harder, and I'm going to show you a few things that I'm not going to show you today. Okay, but it's shown on the video and it's in the book. So doing this thing a different way. Let me give you an example why. Because I may not decide to use surface slider. What does plane of symmetry means? It means that things on that plane do not go to the left and right. What is left and right on this face? Well, it's going to the x. No displacement in x. Look at the coordinate system. No displacement in x. But when you go to this side is neither x, nor y, nor z. This is why in the book and in the video tutorial that you may be looking at from 2 years ago, you notice that I've created local coordinate system, for example, whose x is perpendicular to this, or whose z is perpendicular to that. And I say no displacement in the direction perpendicular, which is either x or z, whatever you arrange. So that was, but if you use surface slider, I don't have to worry about it. Okay. Now, before we regret this thing, let's go ahead and save. File, save management. Your part is saved, but not your analysis. You click on it, save as, in that same folder, lecture 1, section 1, and move this thing out of the way. So I want this name to be just like that. In other words, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7, 8, 9. I think your ID numbers are 9 digits. And then Timoshenko, your last name, Timoshenko. And then lecture 1, section 1, I mean. Rotating, okay, rotating. I wish you could do cut and paste here, but I don't think you can. Disk 3 planes of symmetry. Okay, plane symmetry. Okay, symmetry. So many misspellings here. Symmetry. I'll come to your question. I think somebody's asking something. Okay, analysis. Say okay, and say okay. Okay. Now, I'm going to go back to the stuff that I was doing. If there is something urgent, just speak up, please, because I don't know. You're asking some question, which is great, and somebody else may be answering you, and I don't want to interject in between you or going back and forth between them. Okay, fine. Now, loads. Well, pressure. I don't have a pressure here. Okay. Force. I don't know what the force is. Acceleration. Well, this doesn't sag under its own weight. Oh, but wait. Centrifugal force, where is it coming from? It's coming from some centrifugal acceleration. What is the centrifugal acceleration? Go back to Dr. Altenhoff's course. Isn't it mr omega squared or r omega squared? Radius, what I say, or mass, okay, mass, which you need density, omega squared. Yeah, so maybe it's there, and in fact it is right there. You open it up. This is the apple falling, Newton's apple falling, but this one says rotation force, because rotation force is an acceleration. There you are. You click on it. Okay. Now, centrifugal force is a body force. It doesn't matter what I pick. It's going to take the whole thing. Just like for weight, it took the whole thing. Good. And then it says, what is the value? Okay, I put down here 1079 RPM. This is exactly 113 radians per second. But if you don't want to do that, just type 113 rad underscore second, because I have not changed my unit. It's going to change it to RPM, and it's that number. Okay, axis, rotation axis. It's expecting you to select the rotation axis. Now you can go, or obviously you have to go and select an axis which is down here, right? That's the center of that disk, right? But I didn't make anything at the center of the disk. You may want to go and select this. Oh, you may want to go and select this edge. Well, you can run it and it'll give you garbage, no problem, because it says that it's rotating about that edge. Yeah, if you want something, just go and pick this. It'll run and it'll give you garbage because it's not rotating about that. What I really need is something that I don't have. I need a line here, which I can pick as the center of rotation. So I have to cancel this. I don't have the line. Cancel that. Okay. Now, to get that line, obviously, as soon as you say line, you can't do it in analysis. So let's go back there. Let's go back there in the part. The part is sitting in the back. You can go and draw a line here, or we can also do a fast way of doing it. Notice that at the bottom, there is something called Tools, Axis System. As soon as you click on the axis system, it will create an axis system at the global origin, which is right there, and align with the global coordinate system. You can move that, but I don't want to move it. All I need is a line. And this gives me a line right there. That Z is my line. Say okay. And when you go to your analysis, you see that, oh, it's also here. Okay, so let's go back to that same dialog box. The part. Rotation axis. Now I can select it from the screen. You see this? It puts that thingy that tells you it's rotating right about that. And this is the correct number. And I say okay. Now, before I move on, I want to say something about this bottom one, angular acceleration. Now, notice there's 0 there by default, and I didn't change it. What I said is that this is turning at a constant speed of, I don't know, 113 radians per second. If it's turning at a constant speed, its angular acceleration is 0. If it's going at a constant speed, its angular acceleration is 0. There is a centrifugal force. The more appropriate way of saying this is tangential acceleration is 0. There is a centrifugal one, of course, we know that, but the r omega squared, but angular acceleration is 0. If you were trying to do a problem, for example, this was a disk that starts from the stationary condition, you flip the switch, it started to turn until it reaches, for example, 113 RPM. You not only have to give it the speed at the time that you're interested, finding the stresses, but also the angular acceleration. But I'm assuming magically somehow this reached that velocity and it's turning at that speed. Okay, save. No questions. Okay. Right. So let's go ahead and run. Calculator. Looks like a calculator. It says compute. Don't worry about that. Hopefully we didn't make a mistake. Always pray it worked. So let's look at the deformation. There we are. Well, let's look at the view from the top. View from the top, like that. And the animate. Animate. Isn't that the way it's supposed to work? If it's going at a constant speed, I told you that if you draw a line on the top face and another one on the top face 30 degrees apart, in principle, when this thing rotates, those lines are going to go radially out, but the angle does not change. And this is what it's telling you. And that shouldn't surprise you because you made these planes of symmetry. You made these things surface slider. Things can only move along that line on that surface. That's not surprising. Now, let's look at the deflection. There we are. Very tiny. These are in inches, but very tiny. That doesn't surprise you either. Because look, this is a 1-inch thick piece of steel, shaft basically, that's what it is, which is 1-inch diameter inside, 6-inch diameter outside. It's going at 1,000 RPM. That is nothing. It's go out, it's going to get fattened, but by very little amount. So that's not surprising. Look at the stress. As long as it's below the yield strength of the material, first of all, the promise is going to be here, biggest here. As long as it's below the yield strength of the material of steel, everything is safe for static failure. And notice that this is 281. The yield strength of steel is 30,000 psi. 30,000 psi. This is 281 psi. It's 100 times smaller. Okay. So let's save this. I also want to show you the principal stresses here. So if you go to, this was deformation, this was the von Mises stress, this one is deflection. But if you open it up, right in the middle, it says principal stresses. And if you go scroll closely, you see these, you remember Dr. Green's class, 3 directions. Okay, there we are. So one of them is hoop. For example, if you get closer, this one is hoop, the bigger one. This one is very tiny. Look, just look at the number up there, 0.009. That's the axial one, which is 0, and this one is the radial one, which is something between 0 and the biggest one. Now, but if you want to see only the hoop stress, so you double click on this, or on the tree, there is a branch associated with this graph. You can double click on this branch instead. You go more. Notice that it gives you all components of principal stress. But if you want the biggest one, Dr. Green told you it's called sigma 1, C1. If you want the smallest one, Dr. Green told you that it was C3. If you want the intermediate one, it's C2. Here's the hoop, biggest one. There we are. Look, it looks like tangential stress, principal stress. Excellent. You want to see the radial? Look, by the way, the hoop stress has a value which is around 281, and it drops. It doesn't go to 0. Out here is 66. You already know that. But if you look at, for example, the radial stress, which is C2, notice that there's a 0 here, almost 0 here. See that? These blue almost 0, and it goes to almost 0, and in the middle is the biggest one. It agrees with the structure of this curve. 0 goes to maximum and drops down to 0. Okay. So, are there any questions? Because I would like to go and redo this problem, removing that middle plane of symmetry. I will use the 30-degree sector, but I will remove that middle plane of symmetry. Are there any questions? I guess the answer is no. Okay, so I'm going to kill this. Over here, because I want to make some changes there, and I don't want to destroy the original part, I'm going to I'm going to save this thing under a different part name. So file, save management. This is what I have right now. Save as. Okay, so let's go ahead. How do I want to change the name? Part number, your ID number, your last name, lecture 1, 2 planes of symmetry. So if I make any changes, it's not going to affect the first one. Okay. Now, what is the change that I want to make? I don't want this thing to be half the thickness. I want it to be the actual thickness. Remember in the last week when we did some problems, the block with a hole, remember that? I cut it with planes, and then when I wanted to get those planes back, I went and deactivated those splits or deleted them. Here, I didn't do that. In my sketch, I actually drew the thing that represented the half the height of the thing that I wanted. So what I need to do is to go to that sketch, and instead of this being 0.5, I want it to be 1. And notice that this is going to get fattened up, double the height. You can see that. Save everything. And now we're going to go and create our new analysis file. It is possible to salvage, to spend a, to save a few, maybe a minute or two by going to the other analysis that you saved and make changes there. But it's very iffy if you don't know what you're doing. My suggestion is that here's your part, do it again. Okay, so you go to generative structure analysis. There you are. You refine the mesh here. You remember that? You refine the mesh here. You know what to do. Click on that. Click on this. Use the same thing. Okay. Would you like to see the mesh? There we are. Incidentally, before I go any further, this question came up because in your PDF template, you have to say how many elements you've got. You've got to put number. And people ask me, well, how do I get the number of elements that I have here? Okay, this is what you do. You get the mesh, you put the mesh in front of you, activate it. There we are, it's active, you can see that. You go to this question mark, see that? Analysis tools, this question mark right there, information. You click on it, and it tells you that you have 3,214 elements and that many nodes. Okay, that's the number of elements. Okay, good, good. Now to do the rest of the problem, you have to deactivate this. So deactivate. Okay. So we're going to need a surface slider here. Surface slider on this. Surface slider on that. And surface slider at the bottom. Come on, say something. What do you say? Surface slider. You're awake or not? So here, if you click on it again, it'll take it away. No, not the bottom. Correct. Very good. Now, the centrifugal force or the rotation force, you click on it. It's a body force. It doesn't matter what you pick. Axis of rotation, we already have it right there. This is the z-axis. See this? Okay. This is the RPM that I gave it. Constant velocity right there. And we say okay. All right. Excellent. So this is it. Save it. Don't forget to save it. File, save management. This is the one, save as. Okay, let's use this. This is the old one that I had there. I had it in that folder. Remember that? This is the old one that I don't want to destroy. But at least I can get the name of it. And then instead of 3 planes of symmetry, I can change that into 2. Instead of cut and paste, I say, oh, take this name, and then I changed it. So I have both of them now. And say, okay. All right, so we're going to run this. And let me remind you again, it is a very good idea if you save before running. The reason is this. If you never saved and you ran and it took 1 hour to finish, you're going to be gone, I'm going to be gone. So you want to kill the job. If you kill the job, all the stuff that you have done in the surface slider and low are going to be lost. So people always save before they run. In case they have to kill the job, at least they can go back to their restraints and loads and things like that. Good. Now, and always pray, because it looks like we have done everything. Okay, fine. Run it. That's why I said pray. It didn't run. It tells you there's a problem, possibly because you didn't put enough restraint. In fact, can we ask CATIA maybe help us identify what the issue is? It can't give you the stress, but maybe this deformation is going to help right there, and you can see what happens. This could not have happened before because you took that middle plane of symmetry and you put surface slider on it. This just could not fly away. But right now, I don't have a surface slider. There is nothing that stops this thing from going up and down. Basically, it means that you can't run the problem. Okay. So this is a rigid body motion. We have done problems of this type. There is a fast way of doing it in CATIA. I will not show you that until you come to me, and I'll be glad to share my knowledge with with you. Okay, so I'm going to show you the other way, which was called 1, 2, 3 rule, or some version of it. You know what the issue is here. This cannot go up and down as a rigid body. So all you do, you go and select the user-defined restraint. You select a corner point like that and say, hey, don't go in the direction 2. Direction 3. Don't go up or down, because 0 means 0. No up, no down. And hopefully you fix it. Sometimes you do something, you think it's going to work out, and then you come back, you say, oh, I have to do something else. Now, when you watch the video on your assignment number 2, which is not given to you yet, you haven't done assignment number 1 yet, that's for next week, you will see I made a mistake there. I thought it was going to work, but there was something else I forgot to do. So anyway, just letting you know. I better not get that message, otherwise I forgot something else. Oh, I didn't get it. So show me the deflection right there. Wait a minute, this didn't move at all. What happened? It's not moving at all. Should I panic? The rest of the problem. Okay, my question that I ask is, why is it that when I animate here, I cannot see this thing moving? That was the question. Can somebody help me? Help me, please. Okay, so close, reset the scale, default, there we are, and animate. Yep. Say okay. Can I see the 1 meter stress? Yep, it's the same thing. And the same thing with deflection. Save everything. Now, before we go home, yeah, you guys are good. You guys can go home. I have another lecture later. But here's what I want to show you. Let me get rid of this. Let me get rid of this. And that. May 18, lecture 1, section 1. This is what I did. Remember, I created a part and the analysis. Let's look at it like this. A part with 3 planes of symmetry and the analysis with 3 planes of symmetry. And then a part with 2 planes of symmetry and the analysis with 2 planes of symmetry. So if I had to do this thing, submit all of these, if you're asked to submit both problems, then obviously these are going to go into your GAs folder. On the test, we haven't decided yet, but it could be that we create look, I haven't decided yet, but we'll find out. If hypothetically you have 4 problems to do, we're going to create 4 folders: problem 1, problem 2, problem 3, problem 4. Okay, so the sketch is going to be, the naming is going to be like that, but you're going to call it problem 1, an analysis problem 1, etc. So you put these things in the first folder, which is problem 1, and these things in the second folder, which goes with problem 2. Okay, we haven't decided exactly, but if you organize your work, nothing is overwritten, nothing is lost, and you can upload things quite easily. Okay, folks, are there any questions?